Да, объявление для русскоязычной части аудитории. Лекции на всякий случай будут по-английски, поскольку я еще пока даже не знаю, кто на этот курс записался, а кто нет. Ну и кто-то мне потом писал летом из разных далеких стран, что хотелось бы, чтобы это было транслировалось, чтобы было по-английски. Так что давайте будем по-английски, независимо ни от чего. Я надеюсь, что больших проблем там не будет. Okay, so to begin with, let me say a few words about the subject of the course and about its history. Harmonic analysis deals with function spaces on groups and more generally on homogeneous spaces and with functional algebras on groups and with some special near operators between such spaces and algebras. Chronologically, harmonic analysis goes back to the theory of trigonometric Fourier series, which you probably know about from your second year calculus course. So the theory of Fourier series was founded by Fourier at the beginning of the 19th century. And you probably remember that this theory is about representing sufficiently nice periodic functions on the real line as the following series. So this is the classical trigonometric Fourier series. The functions, the sine and cosine functions which appear in the series are usually called elementary harmonics, and they have numerous physical interpretations. What's special about these functions from the mathematical point of view? Well, to answer this question, it's useful to write the Fourier series in the complex form. So now it runs over the integers. And we have the following series. So this is also quite standard. I hope you remember this from your calculus course. The next step is to observe that a periodic function, so f was assumed to be periodic, a periodic function on the real line is nothing but a function on the circle. So if f is a function on the circle, then we can write its Fourier series in the following simple form. So here, a little z is a complex parameter, and it is related to the real coordinate x in the following simple way. So this is a complex number, moreover it sits on the circle, that is on the unit circle on the complex plane. So let's denote this, we will always denote the circle by bold t. Topologists like to denote it by S1, but for our purposes, this is not just a topological space. It's very essential that this is a topological group. And because of this, it's common to denote this object as bold t in harmonic analysis. Well, equivalently, we can write this decomposition in the following form: ck chi k, where chi k is just z to the power k. And let's now observe that these functions chi k have the following nice algebraic property. So in other words, these functions are group homomorphisms from the circle to itself. In general, if you have a group G, then homomorphisms from G to the circle are usually called unitary characters. Unitary characters of G. If G is a topological group, then characters are usually assumed to be continuous. And if G is abelian, then this set, actually it's also an abelian group, is usually denoted by G hat, and it's called the dual of G. So in summary, we see that the Fourier series of function on the circle can be written in the following form. And why is this so? This is true because we will see shortly that all continuous characters of the circle are of this form. So there are no other characters than these functions characters. So this is a short form of the Fourier series of function on the circle. So from the modern point of view, the theory of trigonometric Fourier series is nothing but harmonic analysis on the circle. And it turns out that many classical results of the theory of trigonometric Fourier series extend to arbitrary compact abelian groups. Well, harmonic analysis is closely related to another classical field of mathematics, namely with representation theory. So representation theory studies representations of groups, that is, homomorphisms from a group to the group of inversible linear operators on a vector space. Many classical groups are actually topological groups, and in this situation, it's natural to consider representations of such groups on topological vector spaces, and in particular on Banach spaces or on Hilbert spaces, and such that these representations satisfy some reasonable continuity assumptions. Well, at the first glance, when we compare Fourier series with such representations, it seems that these subjects are very different. But in fact, they're very closely related for the following reason. For example, if we are mostly interested in representations, and we begin to study representations, and it quickly turns out that many classical representations actually act on function spaces on groups, and on function spaces on homogeneous spaces. And so to study such representations, we have to apply harmonic analysis, which deals with the structure of such spaces. And the other way around, if we are mostly interested in harmonic analysis, so we want to study function spaces on groups, then to study such spaces, it is useful to consider respective representations of groups on these spaces and to try to decompose them into irreducibles. So in summary, it turns out that in many concrete situations, harmonic analysis and representation theory are so closely related that it's almost impossible to distinguish between them. Okay, let's now draw a picture which roughly represents the structure of harmonic analysis and representation theory. So the big rectangle is the class of all locally compact topological groups. Locally compact topological groups. This is the natural setting for harmonic analysis and for representation theory. This class contains two important subclasses, namely the class of compact groups and the class of abelian groups. And a typical example of a group which is both compact and abelian is, of course, the circle. So we already know that the harmonic analysis on the circle is nothing but the theory of trigonometric Fourier series. So this is the beginning of the 19th century. Well, what happens if our group is compact but is no longer abelian? It turns out that in this case, the set of characters can be too small, so it is no longer relevant. However, to get a reasonable substitute for the theory of Fourier series, we must replace characters by irreducible representations, or more exactly by matrix elements of reducible representations. The respective theory was created mostly by Peter and Weil. And this is approximately 1920s. By the way, representation theory of compact groups contains, as a special case, the representation theory of finite groups. Well, some of them are abelian, of course, so I must draw something like this. Representation theory of finite groups. And this is a classical field of mathematics which goes back to the fundamental work of Frobenius and Schur. This is the end of the 19th century. Well, let me say a few words about another generalization of the theory of Fourier series, namely about harmonic analysis on abelian locally compact groups. So what if our group is not necessarily compact, but is still abelian? In this case, it turns out that we still have a rich supply of characters. In particular, they separate the points. But at the same time, it is usually impossible to decompose functions, and even very nice functions, in this form. To get a good substitute of the theory of Fourier series, we must replace here the summation by the integration with respect to a suitable measure. And the respective theory was created in the 1930s, first by Pontryagin, and by Andre Weil, this 1930s. However, the most elegant approach to harmonic analysis on locally compact abelian groups was in fact initiated by Buffon in the 1940s. And this approach is essentially based on the theory of commutative Banach algebras. This approach was further developed by many other brilliant mathematicians, Shilov, Rykov, and by many other people. And it is exactly this part of harmonic analysis which we are going to concentrate on in our course. Maybe, if time permits, at the end of the course we will consider some non-abelian groups as well. But the main emphasis will be on harmonic analysis on locally compact abelian groups, and on the theory of commutative Banach algebras, which plays an essential role in this theory. Okay, so this is our plan. The first or maybe first three lectures, the plan for the first three lectures will be as follows. Before plunging into the general theory, we'll consider some special cases of harmonic analysis, which you are actually familiar with from your calculus courses and from your algebra courses. The first lecture will be about a toy example of harmonic analysis, namely about harmonic analysis on a finite abelian group. This special case is very simple, but at the same time, it already illustrates some basic principles of harmonic analysis. Harmonic analysis on finite abelian groups. Oh, by the way, I forgot to tell about about grading. The grading system will be very simple. We'll have two written take-home assignments. The first one will be approximately at the end of October. The second one will be at the end of December. And the total grade will be calculated by the following formula: 0.3 times the first assignment, let's call it midterm, plus 0.7 times final. Both assignments will be written and take home, so you'll have approximately about 10 days to do them. Okay, so let's now speak about mathematics. First of all, let's adopt the following convention. We will work over the field of complex numbers. So everything will be over the complex numbers. All vector spaces will be over the complex numbers, over all algebras, and all the operators are assumed to be complex linear. Let's now also introduce some notation. The multiplicative group of all non-zero complex numbers will be denoted by C cross. Algebraists like to denote this group by C star, but star is a little bit ambiguous. In functional analysis, star is normally reserved for the dual space, so I'll denote it by C cross. And the unit circle on the complex plane will be denoted by bold T. This is a subgroup in C cross. Well, suppose now that G is a group. At this point is an arbitrary group. Suppose that G is a group, and by definition, a character of G is just a group homomorphism. A group homomorphism chi from G to the multiplicative group of non-zero complex numbers. And an important special case is the case of a unitary character. We say that this character chi is unitary if it takes G to the circle. We are mostly interested in unitary characters. Anyway, if our group is finite, then this condition is satisfied automatically. This is a simple exercise. If G is finite, then all characters of G are unitary. Let's now observe that if we consider the set of all characters, of all unitary characters of G, then this is not just a set. This is also an abelian. This is an abelian group. With respect to the usual pointwise multiplication, you have two characters, chi1 and chi2. We can multiply them pointwise, and the resulting function is also a unitary character. Well, of course, the identity element in this group is the character which is identically 1, and the inverse character of chi is just 1 over chi of x, which is, by the way, equal to chi of x complex conjugate, because chi of x sits on the circle. Okay, let's now assume that G is finite and abelian. assume that G is finite and abelian. In this case, the group of unitary characters of G is denoted by G hat, and it is called the dual of G. Well, let's look at some concrete examples. So, suppose that G is a finite cyclic group generated by an element x0 of order n. And let's denote by un the group of nth roots of unity. Well, this is a subgroup of the circle. And it's a very simple exercise to show that the map from G hat to un, which takes every character chi to chi evaluated at x0, is a group isomorphism. Isomorphism. So since un is also a cyclic group of order n, we deduce that G and G hat are isomorphic. But the isomorphism is not canonical. It depends on the choice of the generator, x0. So what if G is not cyclic? Well, in this case, we have a fairly simple lemma. Essentially an exercise for you. You have two finite abelian groups, G1 and G2. Then the dual of their product is isomorphic to the product of their duals. And the isomorphism is quite explicit. So every character chi of the product goes to its restrictions to the subgroups G1 and G2. This is easily seen to be a group isomorphism. So as a result, we have the following simple proposition. If G is a finite abelian group, then G is isomorphic to 0. But again, the isomorphism is not canonical. This fact is actually parallel to the well-known fact from near algebra, which states that finite dimensional vector space is isomorphic to its dual, the space of linear functionals, but there is no canonical isomorphism. There are many isomorphisms, they depend on the choice of the basis, and none of them is the best one. The proof of this is also very easy, because we know that a finite abelian group is isomorphic to a product of finitely many cyclic groups. And if you apply now the previous exercise, we see that the dual of G is isomorphic to the product of their duals. But we have already calculated the dual of a finite cyclic group, so it is isomorphic to the product of U and 1 to U and K. But they are also cyclic groups of the respective orders, N1 to Nk, and so it is isomorphic to G. And that's it. Okay, let's now look at the second dual, or the bi-dual group, G double hat. So what's this? Well, we know that G hat is also a finite abelian group. So the dual of G hat is well defined. We denote it by G double hat. It turns out that this group is now canonically isomorphic to G in the following way. Let's denote by IG. Well, first of all, let's take a point x in G, and let's denote by epsilon x the respective evaluation character of G hat, given by the following formula. It takes every character chi of G. Well, it's clear that epsilon x is a character, a unitary character of G hat, so it sits in G double hat. And as a result, we get a map, let's denote it by IG, from G to G double hat, which takes every element x to the evaluation character epsilon x. Again, it's immediate from the definition of this map that it's a group homomorphism. A group homomorphism. I claim that this is an isomorphism. And this result is a toy illustration of the Pontryagin duality. Well, I put the quotation marks here because, of course, this result was known long before Plancherel. It's only about finite abelian groups. So if G is a finite abelian group, then the map IJ is an isomorphism between G and G double hat. The proof is essentially based on the following lemma, which roughly states that characters separate the points of G. If X is an element of G and is not equal to the identity of G, then we can always find a character of G such that chi of X is not equal to 1. Well, to prove the lemma, let's first consider the case where G is cyclic, and say generated by x0. In this case, we actually have an injective character. Injective character chi given by the following formula. It takes x0 to the power k to the following number. Well, this is seen to be injective. So this chi works. It applies to any non-trivial element little x. If G is not cyclic, then in general we don't have an injective character, but nevertheless we can always decompose G. In the general case, we can decompose G as the product of finite and many cyclic groups. And this solves the problem, because if we have an element in G different from the identity, then sum of the coordinates of this element is not equal to 1. For example, the first coordinate is not equal to 1. And we find a character on the first subgroup, an injective character on the first subgroup, and extend it trivially to the whole group G. So it is trivial on all other factors. And by construction, it satisfies this condition. Okay, so this completes the proof of the lemma. And now to prove the theorem, let's observe that lemma is, it means exactly that the kernel of our canonical homomorphism Ij is trivial. Ij is a monomorphism. So by construction, the kernel of Ij is the intersection of the kernels of all characters. But by lemma, this intersection is trivial. So Ij is a monomorphism, but on the other hand, we know that the order of G double hat is equal to the order of G, because the order of G hat is already equal to the order of G. And it follows now from the elementary set theory that Ig is an isomorphism. And this completes the proof. Okay, this is a very simple result, but what is essential here is that actually it turns out that this result extends to an arbitrary locally compact abelian group. Okay, let's now discuss another fundamental notion of harmonic analysis, namely the notion of the Fourier transform, again in the context of finite abelian groups. Well, so let's know the space of all functions on G, like this. So fun of G is the space of all complex valued functions on G. We take a function f on G, and we define the Fourier transform of f to be the following function f hat, which is defined on the dual group, and it is given by the following formula: f hat of chi is equal to the following sum. So the sum is taken over all elements in G.
Sorry, why is the order of G to hats equal to the order of G?
Well, we look here. So we know that these groups are isomorphic, G and G hat. So the order of G is equal to the order of G hat. And the order of G hat is equal to the order of G double hat. So they have the same cardinality, and if you have an injective map between two finite sets of the same cardinality, then this map is bijective. Okay, so this is the Fourier transform of f. This construction makes sense for any function f on G. So as a result, we can introduce the following map, as denoted by f script f, which acts from the space of all functions on G to the space of functions on G hat. And this map takes every function little f to little f hat. And this map f is called the Fourier transform of G. Okay, by the way, there is another common definition of the Fourier transform, which is not equivalent to ours, but which is closely related to it. Another definition. Sometimes you will find the following formula: f hat of chi is equal to the sum over x, f of x, chi of x complex conjugate. Of course, this is not equivalent to our definition, but it is closely related. we can observe that chi of x complex conjugate is, we can just replace chi by chi inverse. This is the same number. So our definition and this definition are related by replacing chi by chi inverse. In some situations, this is convenient. From my point of view, this looks much more natural. So we'll use this formula as the definition of the Fourier transform. Okay, let's now look at some examples. Take a point x in G and consider the respective delta function, delta x. So this is the function which is equal to 1 at x and 0 elsewhere. Let's calculate the Fourier transform of delta x. Well, delta x hat chi is equal to the following sum. And we see that only one sum survives here, namely chi of x. And if we use our previous notation, we see that this is epsilon x applied to chi. So as a result, we see that the Fourier transform of delta x is the evaluation character epsilon x. Okay, now it's natural to ask what happens if we take the Fourier transform of a character. To answer this question, we need the following simple lemma. If chi is a character of G, which is not identically 1, then the following sum, chi of x over the group, is equal to 0. Well, this is very easy. Since chi is not identically 1, let's take a point where it is not equal to 1, take y, such that chi of y is not equal to 1. And let's multiply this expression by chi of 1. Well, since chi is a group homomorphism, we see that this is equal to the following sum, chi of yx. But of course, the left translation is a bijection of G onto itself. So x runs over G, yx also runs over G. And so we can replace here yx just by x. The sum will be the same. Sum is the same. So we now compare this and this, and we see that since chi of y is not equal to 1, the only possibility for this equality is the case where the sum is equal to 0. And this completes the proof.
Sorry, could you repeat the last step?
This one, or this one. This one. Oh, yes.
The next one.
This one.
Yeah.
Well, if you have two numbers a and b, and ab is equal to b, and a is not equal to 1, then b is equal to 0. Okay. Very easy. Very easy. This is a, and this is b. Okay, let's now look at the space of all functions on G, and let's introduce an inner product. Inner product on the space of functions on G. So we define it by the following simple formula. the inner product of two functions f and g is the following sum: f of x, g of x complex conjugate. So clearly this is an inner product, and it makes the space of functions on G into a finite dimensional Hilbert space. We now have the following result. A proposition. The set of characters of G, so it is a subset in fun of G, and I claim that this set is an orthogonal basis. Orthogonal basis in form of G. And moreover, the norm, the Hilbert norm of every character, that is the square root of the inner product of chi by itself, is equal to the square root of m, where m is the order of G. Well, indeed, if you take two characters, say chi1 and chi2, which are not equal to each other, and if you calculate their inner product, so we have the following sum. Chi2 of x is, well, it's on the circle, so it is just chi2 inverse of x. So we can write this sum in the following form. And this product chi1 times chi2 inverse is again a character. So we apply our lemma to this character. It is not identically 1 by assumption. And we get 0 by lemma. We get 0, and so we see that G hat is an orthogonal set in form G. We will now calculate the norm. Well, the square of the norm of every character. This is the inner product of chi by itself. Well, this is just the sum, but chi is a unitary character, so this number is equal to 1, and the whole sum is equal to n. And this proves the second statement. Finally, why is it a basis? Well, it's a basis for a simple reason that the cardinality of G hat is equal to the cardinality of G, that is the n, but this is exactly the dimension of fun of G. So we see that G hat is an orthogonal set of non-zero elements, and its cardinality is exactly the dimension, so it is a basis. G is a basis of form of G. And this completes the proof. By using this result, we can now easily calculate the Fourier transform of a character. So we take a character, chi of G, and we calculate the Fourier transform of chi. So it is a function on G hat. And by definition, this is equal to the following sum. Phi of x, chi of x, phi of x, phi of x, chi of x. This is nothing but the inner product of phi and chi complex conjugate, or equivalently of phi and chi inverse. But we already know that the set of all characters is orthogonal. So this is equal to 0 if these characters are different, if phi is not equal to chi inverse, and it is equal to n if they are the same. In other words, we see that the Fourier transform of chi is n times the delta function concentrated at x inverse. It's useful to compare this result with our previous formula. So the Fourier transform of a delta function is a character, and the Fourier transform of a character is a delta function multiplied by n. Combining these two examples, we come to an important result, which is a very special case of the Plancherel theorem. But before I state this result, let's introduce a suitable inner product on the space of functions on the dual group. So we equip the space of functions on the dual group fun of g hat. We define an inner product as follows. Well, it seems natural to take this a similar sum of chi, g of chi of its conjugate over all characters. But for technical reasons, it will be convenient to put a constant 1 over n here. And if we equip the space with such an inner product, then we naturally come to the following result, which is a very special case of the Plancherel theorem. Which states that the Fourier transform is a unitary isomorphism between the respective finite dimensional Hilbert spaces. Unitary isomorphism. That is, the bijection which preserves the inner product. The proof is very easy because we already know that if we consider all the characters of G and divide every character by the square root of n, then we get an orthonormal basis in the space of all functions on G. Orthonormal basis in form of G. This follows from this proposition. On the other hand, if we consider delta functions on the dual group and multiply each of them by the square root of n, then we get an orthonormal basis in the space of functions on the dual group. Well, indeed, this is immediate from this formula for the inner product. So only one summand here survives, and it is equal to the square root of n times the square root of n, which is equal to n, and we divide by n and get 1. So this is an orthonormal basis. And we already know that the Fourier transform takes the first orthonormal basis and the second one. And that's it. So a linear map between two finite dimensional Hilbert spaces, which takes an orthonormal basis to an orthonormal basis, is a unitary isomorphism. And this completes the proof. In fact, this result is also very fundamental. Like Pontryagin duality, it extends to an arbitrary locally compact abelian group. But of course, in this general case, it is highly non-trivial. So one of the goals of our course is to prove the Plancherel theorem, the Pontryagin duality, and some other fundamental results for arbitrary locally compact abelian groups. Okay, let's now compare the Fourier transform. Oh, by the way, before we speak about Fourier transform of the dual group, let me make a little remark about the role of this multiplicative constant 1 over n here. In fact, the correct way of looking at the Fourier transform is that the summation in this formula is actually an integration with respect to the counting measure. So the Fourier transform of f can be written as the following integral. Of g, where mu is the counting measure. Which is uniquely determined by the requirement that the measure of every point is equal to 1. Well, clearly the integral with respect to such a measure is just the summation. So the space of all functions on G can be interpreted as the space of square integrable functions on G with respect to the counting measure. And the space of all functions of the dual group is also the space of square integrable functions with respect to a suitable measure, mu hat, which is defined to be the counting measure divided by n. And this measure is called the dual measure of mu. So if we put g hat with this measure, the counting measure divided by n, then we see that the function, the respective L2 spaces are unitarily isomorphic, and the isomorphism, the complete isomorphism is the Fourier transform. Actually, another approach, an alternative approach to the Fourier transform, could be as follows. We could take, for mu, we could take the counting measure divided by the square root of n. So in other words, we could take our original formula for the Fourier transform and put the multiplicative constant 1 over the square root of n in front of the summation sign. And it turns out, actually, it easily follows from our results that in this case, the respective dual measure has exactly the same form. It's the counting measure on g hat divided by the square root of n. Well, this approach to the Fourier transform is probably aesthetically more attractive because of the symmetry between the measure and the dual. But on the other hand, from my point of view, our original approach is more natural. So we pretend that we didn't know from the very beginning about this multiplicative constant. So in this case, if mu is the usual counting measure, then the dual measure is the counting measure divided by n. But in fact, this is not very essential because the two versions of the Fourier transform are essentially equivalent. Modulo suitable multiplicative constants. Okay, let's now compare the Fourier transform of G with the Fourier transform of G hat. So we already know that G and G hat are canonically isomorphic. So G and G double hat are canonically isomorphic. So let's identify them by
identify G and G double hat canonically. Then we have two maps which act in the opposite directions. The Fourier transform of G acts from the space of functions on G to the space of functions on G hat. And the Fourier transform of the dual group acts in the opposite direction. The initial question is, how are they related to each other? The relation is very simple. First of all, let's write an explicit formula for f on G hat. We still remember that f G hat, from the point of view from the point of view of the Plancherel theorem, G hat is equipped with a countermeasure divided by n. So it is natural to define the Fourier transform on the dual group by the following formula. The respective function G hat is the following sum: G of chi of x, and divided by n, because this factor appears in our measure on G hat, and it appears actually in the Plancherel theorem. And let's also introduce some more notation. We denote by SG the following self-map of the space of functions of G, which is given by the following simple formula. It takes f to f of x inverse. So it is induced by the inversion map on G. Now we have the following simple but useful result. This is the inversion formula for the Fourier transform. So I claim that if we first apply fg and then apply fg hat, then we get sg. In other words, for every function f of g, every function on g can be reconstructed from its Fourier transform by means of the following formula. Well, this is not correct, because this formula means that fg hat composed with fg is the identical map. It is not identical, it is sg. But so to make it correct, we can simply put the complex conjugation here, because chi of x complex conjugate is chi inverse of x, that is sg applied to f of x. So this is the Fourier inversion formula. And again, the proof is very easy, because we have already calculated the Fourier transform of the delta function and of every character. Well, indeed, we start with a delta function and apply the Fourier transform, fg, we get the evaluation character epsilon x. If we now apply the Fourier transform of the dual group, fg hat, well, we know that the Fourier transform of a character is the respective delta function evaluated at the inverse character and multiplied by n. But we have the constant 1 over n here, so there is no need to multiply by n, and we get a delta function concentrated at epsilon x inverse. But our convention is that G and G hat, G double hat and G are canonically identified, so this is nothing but delta x inverse. So we see that for delta functions, this formula is true, and since they form a basis in the space of all functions on G, we see that the formula is always true. It is true for every function f of g. Again, in the case of finite abelian group, this is very simple, but what is important is that this result also extends to arbitrary locally compact abelian groups. In conclusion, let's discuss, we still have some time. In conclusion, let's discuss a useful algebraic property of the Fourier transform. It turns out that the Fourier transform is an algebra homomorphism with respect to a suitable multiplication of functions. First of all, let me explain what I mean by an algebra. Well, by an algebra, I always mean associative algebra over the complex numbers. That is an associative ring together with a vector space structure. Together with a vector space structure. Such that the multiplication on A is bilinear over the complex numbers. In general, our algebras are not assumed to have an identity. And an algebra with an identity is called a unital algebra. Let's say that A is unital if it has an identity element. And we will see shortly that many natural algebras, which in particular the algebras which appear in the context of harmonic analysis, are not unital. So this is life. This is one of the main reasons why in the context of harmonic analysis and in the context of functional analysis, normally algebras are not assumed to be unital. Just because there are many natural non-unital examples. If we have two algebras A and B, then an algebra homomorphism phi from A to B is a ring homomorphism, which is a linear map, which is linear over the complex numbers. And if A and B are unital, then it's natural to consider those homomorphisms which preserve their identity. So if A and B are unital, then we say that phi is unital if it takes the identity of A to the identity of B. Let's now briefly recall what a group algebra is. Suppose that G is a group. And let's denote by CG a vector space. With such that G is a basis of the space. Such that G is a basis of CG. So it's convenient to look at the space as a space of all linear combinations, of formal linear combinations of elements of G. Say alpha x, x, where alpha x are arbitrary complex numbers. But of course, we assume that all but finite and many of them are equal to 0. So all but finite and many x in G. This space has initial multiplication. small cg. It is uniquely determined, let's denote it by star. And it is uniquely determined by the requirement that it extends the multiplication on G. If we take coordinates of G, then their product in this algebra is equal to their product in G. So as a result, we get an algebra, and this is the group algebra. The group algebra of G. So this is a very classical object. Let's now assume that G is finite. Assume that G is finite. In this case, this condition is satisfied automatically. So we may identify, as a vector space, Cg may be identified with the space of all functions on G. So we have a vector space isomorphism, as denoted by alpha, between the group algebra and the space of all functions on G, which takes every element x in G to the respective delta function. We can now equip the space of all functions on G with a multiplication, which is called convolution. By definition, the convolution of two functions f and g is given by the following simple formula. So we consider the images of f and g in the group algebra, alpha inverse of f. We multiply them in the group algebra, and then apply alpha. So basically, this is just the product in C of G transferred to the space of functions. So as a result, the space of functions becomes an algebra with respect to the convolution product. Let's denote it by from star G. This is the convolution algebra of G. By the way, the Russian for convolution is svertka. There is a useful simple formula for the convolution. So explicitly, this is a little exercise for you. Explicitly, the convolution of two functions f and g is given by the following formula. F star g evaluated at x is equal to the following sum, or y, f of y, g of y inverse x. Then we now get the following result, the theorem. The Fourier transform, so again we assume that G is a finite abelian group. G is a finite abelian group. And then the Fourier transform of G is an algebra homomorphism from the convolution algebra of G to the algebra of functions of G hat, where the algebra of functions on G hat is equipped with the usual pointwise product. Function of G hat is equipped with the pointwise product. In other words, we have the following formula. The Fourier transform of the convolution is equal to the pointwise product of the Fourier transforms. the proof is just a line. Clearly, it's enough to prove this equality for a suitable basis in fun of G. So let's take the basis consisting of delta functions. Well, by definition, the convolution of delta functions is the delta function concentrated at x, y. And we know that the Fourier transform of a delta function is the respective evaluation character, epsilon xy. But epsilon xy is easily seen to be equal to the pointwise product of epsilon x and epsilon y. That is, to the pointwise product of delta x hat and delta y hat. And this completes the proof. So the Fourier transform is an algebra homomorphism with respect to the convolution product here and the pointwise multiplication here. Okay, so that's all for today. And that's all I wanted to tell you about harmonic analysis on finite abelian groups. You see that this part of harmonic analysis is very easy, but nevertheless I hope that it illustrates many fundamental principles of harmonic analysis. So the Plancherel theorem, the Pontryagin duality, the inversion formula, and this result, all of them are extended to arbitrary lower than compact abelian groups.